All right. Hey everyone. So for today, I'm just going to be going over the quiz, and I think that'll be a decent enough review of everything that we've covered so far. And I might talk about some things at the end, but I'm not sure yet. But for now, I'll just be going over the quiz and just kind of talking about things in general, kind of helping you reinforce some of the concepts that we've already discussed. So for the first question, I asked you guys to draw the Lewis structure and the line angle, if it was possible, um, for the following molecules. So for the first one, we have C2H4O2. And if you recall, the first step to drawing Lewis structure, well, it could be two things you could do. You could start off by simply just already drawing the carbons, right? We always said that carbons are the backbone of the molecule. So it's really safe to assume that we can just start off with the carbons and they're usually bonded together and then everything else branches off of them. In the case that you don't have carbons, a simple rule applies here. It's that you tend to have the least electronegative atoms in the middle of the molecule and everything else branching outwards. So the more electronegative things are always coming off. Okay, so the first step is to calculate the number of electrons using the valence electrons that each atom contributes. So number of electrons is equal to each atom's valence electrons. And here there's a neutral molecule, no charge was indicated, so we don't include that. So you have 2 carbons, so that's 4 times 2. And then we have 4 hydrogens, all right, so that's just 1 each. And then 2 oxygens, so that's 6 times 2. Okay, so this is 8, 4, 12. Okay, so I have 12, 12, 24. All right, this number is just going to help me make a better decision about, it's going to help me check my guess, right? So the way this usually works, you kind of can start with the carbons and then you kind of have to think about like what would be the best setup for this molecule, like what you think it would look like. So just give your best guess, an educated guess, and then just go for it. So I'm gonna draw one that I saw a lot as I was grading this, and it's not bad to do. It's a very safe way to start, and you kind of just divvy up everything. You make everything even, right? I give every carbon the equal number of things. So I have 2 carbons, 4 hydrogens, and then 2 oxygens, okay? And as Renee said in class, we're just going to we're going to fill everything up, okay? We're not going to look at double bonds or anything yet. So I'm going to give everything octet, all right? Obviously, this is right away wrong, first off, because these oxygens would have negative charges if you calculate the formal charge. So this would have a negative charge of 2 overall on the molecule. But that's one way to quickly see it's wrong. And another way is just to count the number of electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have an extra pair of electrons, okay? So the thing that's off about this is that normally when we, at this point, right, when we have too many, once we've given everything lone pairs, we usually turn one of these lone pairs into a double bond, and then that means something on the carbon has to go. But here we have all sigma bonds to things, and we can't remove those. Those are in our proposed molecule. Those are constant. We can't change that. So turning one of these into a double bond and then taking off, a bond somewhere else because the carbon is going to get extra doesn't really work here. And even if you were able to do that, we still have the other side that has a negative charge, and like I said, our molecule is neutral. So those are some things you have to consider. So at this point, this means that we need to consider a new what we think the molecule will look like. Okay, so I'm just gonna draw the correct answer. Okay, so this is the correct answer. All right. Lone pairs. All right, so let's talk about this. So how can I go from starting off with the wrong answer to the right answer? So I know right away that from our previous one, which is very common that I saw a lot of people do this, we know this is wrong. There's no way that we can, modify this and change it, or, make double bonds to change this up and make it better. So the only way that we can, do this is by completely shifting around where the bonding is. So I need to move, what it seems like, I need to move the hydrogens around, okay? So my first time, I tried putting everything even, putting the hydrogens 2 on each. Now, let's try, moving more hydrogens onto 1 carbon, okay? How about let's try putting maximizing the number of hydrogens on this carbon over here while having it still bonded to this carbon, obviously. And then everything else will fill in. So if you put 3 hydrogens over here and then you fill in everything else, this is what you should get, okay? So this is the answer, and I can show you if you were like to do it step by step with how we did it before. So if I start off putting the hydrogens, right? And then let's say I put the oxygen, gave everything the max, right? Okay, so I'm still missing 1 hydrogen, so the hydrogen has to go on one of these, right? And we know that we don't have any negative charges, okay? So I'm gonna bond the hydrogen to one of these oxygens. Doesn't matter which one, okay? And now we can count our electrons at this point. We still haven't dealt with this negative charge over here. Okay, so I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, so I have 24 now, but I still have a negative charge. So, and another thing is this carbon doesn't have full octet. So that's another thing. So I've already fully bonded the hydrogen, and I don't have anything else to bond over here. So the only other option is to make this a double bond. Okay, so under that logic, we can arrive at the right answer. And I understand like there's a lot of like, assuming and kind of like outside knowledge that you kind of need sometimes for these low structures, and that's really how it is. You'll get used to seeing different structures, seeing different like groups on molecules, and you'll know how they look like right away. Usually you won't have to go through all these crazy steps to figure out how a molecule looks like. You just kind of, with what you know already, what you're familiar with, and then just build it. So so if you ever see, again, when you see 2 oxygens on a molecule like this, or a COOH group, or the COO minus group. This is the base form of it, and this is the acid form, okay? So if you see the COOH group, right away this always means it's going to be a carboxylic acid. This is the carboxylic acid group. So if you ever have trouble with, figuring out all this, you can easily just do this and put the carboxylic acid group somewhere, okay? So there's that. I hope that takes care of that one. Okay, let's see. Now for the next problem, we have C6. Come on, C6H6. And this one was kind of tricky because you guys haven't really done rings yet. And I give you guys the hint that it's a ring, okay? And a lot of you actually got this one to my surprise. I'm not saying that I was underestimating you guys, but I was trying to like be tricky on this quiz for your own sake. So I already said it's a ring, okay? And look like this. I just remembered that I forgot to draw the line angle for the last problem. But if you want to draw the line angle for the last problem, it would simply look like this. Okay, that's number 1. Okay, so there's the line angle already so far. I'm building it. I have 6 carbons, which I've already used, drawn them very crappily. And now I need to add my 6 hydrogens, okay? Now, straight off the bat, what you could do, have 6 carbons, have 6 hydrogens. Let me give a hydrogen to each carbon, okay? And we'll calculate the number of electrons very soon. So I have 6 hydrogens and 6 carbons, okay? but each carbon is now still missing one bond. It's still missing 2 electrons. So the way I remedy that is by adding double bonds. Okay, and it doesn't matter whether you put the double bonds, both these structures are correct. Okay, you can put the double bonds like this. Right now I drew it like that. You can also draw it like this. Okay, doesn't matter. It's the same molecule. All right. This molecule is called a benzene ring. This is much more important in ORGO too, but I just wanted to give you guys a tricky problem on purpose. The number of electrons, right? We have 6 carbons, so that's 6 times 4 plus 6. Okay, so that's 24 plus 6, that's 30. So now we can count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, right? Before I added double bonds, if you were stuck, count the number of electrons, and you would have seen that I obviously don't have enough electrons, and I also don't have octet on every single carbon. So the only thing left to do to use up those electrons, we don't have any other hydrogens, we don't have anything else, we don't have any other atoms. So the only thing left to do is to add double bonds. Okay? That's your last option. That was not that bad. And the next one is O3. So O3 is ozone. Okay? And it's obviously just 3 oxygens bonded together. And total number of electrons is just 6 times 3, which is 18. Okay? And always note that it's neutral. Okay? Always check the charge on these molecules. It helps you a lot to figure some things out if you're still having trouble with that. So let's start with doing what Renee does. So she fills in everything, max. Just adds lone pairs once we put the bonds. So I have everything at max now, and I'm pretty sure that our molecule has way too many electrons. So let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay? So I have 20 electrons. I only need 18. I only have 18 to work with. That means I do this. I take one of the lone pairs and I bring it and I make a double bond, and then I get rid of one of the lone pairs over here. Okay, on the other atom. So it's always between the two atoms that you're working with. One of them you turn into a double bond, and then the other atom you get rid of one of its bonds or its lone pairs. Usually it's a lone pair. Okay, so now I have this. Now let's check. Okay, I have 18, so this is, I still have 2 over here. 2, 4, 6, 8, 10, 12, 14, 16, 18. Perfect, okay? Now, I said before that sometimes you will arrive at the right number, but your molecule still won't be correct because you might have a charge somewhere, or yeah, it's usually charge. Sometimes your molecule will have the right number of electrons being used, everything's fine, except the fact that you've created a separation of charge or too many charges, or your atom, your molecule that you're proposing is now charged and it was not. Okay, so here we have neutral, so we need to keep in mind. So now, the way to check that is to find the formal charge. Okay, so formal charge is the next question, but formal charge is just the number of valence electrons minus the electrons that are held by that atom. So let's check the formal charge of each one. So for this oxygen, I have 6 minus 1, 2, 3, 4, 5, because it's like this. There are 2 electrons like this. So 1, 2, 3, 4, 5, 6. So this one is 0. It's neutral. Okay, let's check this one. 6 minus 1, 2, 3, 4, 5. So 6 minus 5, obviously, not dumb, is 1. Okay? So this one's positive, right? And then now let's check this one. So this is going to be 6 minus all these. So 6 minus 1, 2, 3, 4, 5, 6, 7. This one's negative 1. Okay? Now, at first you might be like, okay, that's really weird. You know, I have charges now. I'm not supposed to have charges. But the negative 1 and the 1 cancel each other out. So the molecule overall is still neutral. And this is the correct form of it. And this is also the line angle. Okay? Only with carbons do you draw them like this. Okay? All right, moving on. Let's see. Next question, it says, how is formal charge calculated? So, formal charge. Formal charge is easy calculation that we just do to help us know what the charge of the atom is in a molecule. So, all it is you take the valence electrons, and this is the column number for whatever column the atom is in, and then you subtract from it, so valence electrons minus, in parentheses or brackets or whatever, that you can either say it's the electrons held, or you can say is the individual electrons in each lone pair plus a single electron from each bond. Now it's a really long definition, and I'm just over explaining it in the formula, but yeah, this will get you the right answer every time. So let's look at some examples really quick. Okay, so if I have a carbon, okay, and let's say this is our carbon, okay, it has octet, right? 2, 4, 6, 8, wonderful. But what's the charge on it, right? So the charge on this carbon is going to be its valence electron number or column number, right? 4, right? It's actually the column number. It's the column number minus 10. So column number minus 10. For the column that carbon's in, it's 14 minus 10 gives you 4. Okay. The valence electrons for carbon is 4, and now I start subtracting the individually held electrons by this carbon. Okay. So that is 1, 2, 3, 4, 5. 4 minus 5. And that's negative 1. Okay. So very easy. Very easy. Let's look at oxygen. All right, oxygen has a valence electron number of 6, or it's in column 16, minus 10, blah, blah, blah. Okay, so let's look at this form of an oxygen. Okay, oxygen looks like this. Let's say this was our oxygen that was bonded in a molecule, right? And let's say whatever carbon's coming off over here, blah, blah. Okay, so what's the formal charge of this? It's 6 minus 1, 2, 3, 4. And this is a bond right here, okay? 5, 6. So 6 minus 6, this is 0, neutral, okay? So pretty easy. And now I'm just going to give some examples, just something that if you guys are still having trouble with this, you know, normally as you go on through ORGO, you never have to, you know, do these things again. You just quickly see a molecule and you see its atoms and you see what kind of bonding it has, and you can quickly tell what's positive, what's negative, what's going on over here. So formal charges of common atoms, right? All right, so I'm going to start with oxygen, okay? So oxygen has 3 common forms, okay? I'm going to start with the neutral form, and then I'm going to go to the positive form, and then I'm going to go to the negative form, okay? So for oxygen, the neutral form is always going to look like this. Oxygen is always going to have 2 bonds and 2 lone pairs, okay? It can also look like this, double bond, and like this, okay? Bond into one thing, right? This is the oxygen, this is just a carbon over here, and whatever you can have over here. So 2 bonds and 2 lone pairs, okay? So for oxygen's positive form, it's going to be 1 more bond and 1 less lone pair. So that means I either have, so I have a triple bond essentially. So I have a triple bond, there's oxygen, and I have 1 lone pair, right? So 6 minus 1, 2, 3, 4, 5. 6 minus 5, that gives me a positive 1. This is the positive 1 version of oxygen, okay? Not that common. Okay, and now we have the negative version, a very common form of oxygen, right? Oxygen is electronegative, it takes on negative charge, so you can understand why this is a common form. So it's the complete opposite. So instead of having 1 extra bond from the neutral state, it has 1 extra lone pair. So it has 3 lone pairs and 1 bond, okay? So this is the negative form of oxygen. And this will be very handy, just instantly. If you see these forms, you know neutral, positive, negative. All right, now let's look at nitrogen. Okay, nitrogen. What's nitrogen? Valence number is 6. This one is 5. That's not a 5. Okay, 5. So for nitrogen, nitrogen likes to have 3 bonds and 1 lone pair. So this is 5 minus 1, 2, 3, 4, 5. So that's neutral. This is how nitrogen likes to be. And then the positive version of nitrogen, just as with oxygen, to make it positive, I turn a lone pair into a bond. Okay? So that makes sense because the atom, when you turn a lone pair into a bond, instead of having ownership over 2 electrons, it now shares those 2 electrons and only has ownership over 1. Okay? So that makes a lot of sense. So now it has, turning this into a bond, so essentially it just looks like this. 4 bonds on nitrogen is the positive version. So 5 minus 1, 2, 3, 4, 1. Okay? And the negative version of nitrogen is just the opposite, so I turn one of the bonds into a lone pair. So I have 2 lone pairs of nitrogen and 2 bonds. So 5 minus 1, 2, 3, 4, 5, 6. 5 minus 6, negative 1. Okay? So especially with nitrogen, I think people get confused with nitrogen because I haven't done a lot of nitrogen yet. So it's kind of tricky sometimes. And then last one, carbon, we all know. So for the neutral state, carbon has valence electron 4. It's 4 bonds. Ugh, that's ugly. Okay. Carbon has 4 bonds. The positive state, okay, carbon has, yeah, it has a 1 less bond than it needs, okay? Because obviously it doesn't have any lone pairs, so I can't turn a lone pair into a bond. I just have 1 bond is missing, okay? That's usually how we see a carbo or carbocation, right? And then for the carbanion, or negatively charged carbon, it's 3 bonds and 1 lone pair, okay? So these are your most common, just take a glance, write it down, whatever, pause the video, and just get very familiar with these forms, okay? But overall, just know how to calculate formal charts. Sometimes you will use it, when you want to see like a random atom on a molecule, and you just want to see what its charge is, and it's not given. Bean didn't tell you, wasn't indicated to you. Just be aware of that. She might not always indicate charges, but you're responsible for being able to see and visualize quickly and know if there's a charge or not. All right. Next question is, why do molecules perform resonance? When can it occur? Why, res, and when? Okay. So what is resonance? Resonance is when a molecule moves its free electrons around the entirety of the molecule or part of the molecule. Okay, so why do molecules perform resonance? Resonance performed or occurs so that molecules can achieve a lower energy state, okay, and become more stable. The lower energy and more stable are synonymous, right? And this is done by creating a hybrid structure that combines all the resonance forms, okay? And resonance occurs, right, it's being weird, occurs when we have lone pairs and pi bonds. So pi bonds are double bonds. So when we have lone pairs and pi bonds and, ideally a charge or a positive charge, a negative charge or a positive charge, those charges or the bonds or lone pairs can move around and they can flow across the molecule. So it only occurs when we have the pi bonds and lone pairs because they allow the electrons to move around. Okay, but if you have, for example, I'm going to draw an example where we can't have resonance. Say I have a negative charge on a carbon over here, okay? And let's say I had a double bond over here, right? Can I do resonance over here? No. Why not? Because the very next adjacent carbon, this bond over here, is not a pi bond. So the lone pairs cannot flow into this bond over here and allow these to be pushed out. Okay, you have to have an adjacent, pathway for the electrons to flow. If you don't have that pathway, then you can't have resonance. All right, and another way of saying this is that this carbon over here is fully octet and no double bonds, so you cannot add an extra bond over here. This will make the molecule more unstable. All right. Okay, so that's the answer to that one. And now let's move on to the resonance problems. Okay, so a lot of mistakes on these, but a lot of good tries. We'll talk about some things that I wanted to point out with these problems that I didn't get a chance to in class. The first one, problem A, we have this molecule over here. I have a positive charge on this carbon over here. I have a double bond, and then I have a nitrogen. Okay, before you start, I want everyone, whenever they're doing a resonance problem or an acid, base problem, always to take a look at your molecule and look at check off three things. Do I have an oxygen? Do I have double bonds? Do I have a nitrogen? And do these things have free lone pairs, right? It doesn't have to necessarily be oxygen or nitrogen, but these are typically what you have on a molecule that can donate lone pairs. So I need to look and see, okay, I have an oxygen over here, I have a nitrogen over here, I have a double bond over here, and then I need to look at that with respect to where my charge is, okay? So let's start. So I've drawn out the lone pairs, right? And I know the lone pairs are here because I understand formal charge, and I know that the molecule is neutral. Nothing has not been indicated that it's charged on any of these atoms over here. So neutral state for oxygen, 2 lone pairs, 2 bonds. Neutral state for nitrogen, 3 bonds and 1 lone pair. Okay, so now I need to see what can I resonate. How can I resonate? So the first thing I look at when I see this, I'm like, oh, I have an oxygen over here. So I have an oxygen and it's directly adjacent to the positive charge. And you can resonate this lone pair over here to fully occupy this positive charge over here, this empty, not fully filled octet. And so that would give this structure over here. So I have 1 lone pair remaining, and I formed a double bond right there. And I'm just going to draw this as NH2 from now on. Okay, and I have a double bond right here. That's what I have right now. But never forget, okay, Also note that I drew the arrow. A lot of you forgot to draw arrows and they just drew the next resonance state, and maybe I didn't emphasize that enough, but it's not optional to draw the arrow. You have to draw the arrow. You have to show how the electrons flow from one place to another. You have to show it. Okay, so I showed the electrons moving them here, I circled them, and I drew an arrow out to the bond that it's going to. Okay, and the bond, so the oxygen lost lost an electron to form a bond over here. Okay, it lost these electrons. It still owns one, but it's sharing one. So now the formal charge on this carbon is now positive. Okay, and you can calculate the formal charge by just counting the number of electrons. But 3 bonds and 1 lone pair. That's what a positive charged oxygen looks like. Charge is never destroyed unless you have a reaction. But here you're resonating, not reacting things. So the charge is going to be present somewhere. You have to keep that in mind. So can I do anything after this? Can I aside from going back to what I started with, can I do anything else? Can I go in a different direction? Can I keep flowing? No, right? So I'm basically done here. So this is one path of the resonance, right? It can go back to this form and then we can have a different path. So I'm going to call this path A. And that's what you should be doing on your exam as well. And you can even label this as arrow A, just to be very clear when someone is grading your exam that this arrow is for this path and I'm about to show another arrow for a different path. So I said we have a double bond and we have nitrogen, okay? Nitrogen obviously can't reach over there, but what can reach is this double bond right here. The double bond can come and swing, right? I'm going to draw a line out of the double bond to the bond where the carbon, the positive charge is attached. Okay, so this double bond is going to come over here and it's going to fill this octet, but when it leaves, it's going to create a new positive charge, and that's what resonance is all about. We're just moving the charge around, we're not making it disappear. The oxygen looks like this because we're not doing that. I'll call this B, right? B. And I said I have a double bond right here. That means I have a positive charge over here now. NH2. Okay, so now my positive charge is over here. Can I resonate this again? Well, do I have anything besides going back to the previous one? Yes, I do. I have this lone pair right here that I can work with. So this lone pair can come over here and fill the octet of this carbon over here. So I look like this now. Double bond, NH2. And now nitrogen is positive. Okay, I don't have to calculate the formal charge every time, but I know that when I lose a lone pair and I turn it into a single bond, right, or double bond in this case, another bond, I'm going to become positive. Okay, so I just know that, and you can verify that by checking the formal charge. All right, so do I have anything else that I can do? No, I'm at the edge of my molecule and there's nothing else. The hydrogens can't do anything. I'm done here. Okay, so at this point, you're gonna put a bracket around your resonance structures. Okay, or you could even, since there are 2 paths, put upside down bracket or whatever, something like that. You'll see how it looks on an old exam, and you can do that. But that's not that important. Just make sure you have the bracket. Okay. What was I gonna say? Okay. Yeah. So I think that's it for this one. We just have to pay attention to where we have things that have lone pairs and where we have double bonds. That's what allows us to resonate. So I need to find all the places where I have free lone pairs, so like oxygens, nitrogens, and I need to see where I have double bonds or triple bonds even, okay? So I have double bonds and I have both 2 atoms that have lone pairs on them. So I need to consider this in all my resonance structures that I can form, okay? And you can have different paths. It doesn't necessarily have to be one single path, right? And both of them are important paths, right? So now the big question is, which one of these is the major form of the molecule, right? The major form that exists while it's resonating. So how do we look at this? How do we determine this? Well, first we can compare atoms, and that's just the main thing that we do. We compare the atoms, and we look at first we look at their electronegativity. So here's my crappy periodic table, and let's say I have carbon over here, nitrogen, oxygen, fluorine, sulfur, whatever. Okay, let's say right now I'm comparing these two forms of the molecule. Okay, comparing this one, and you always look at where the positive charge is. So I know which one is going to be the major form of the resonance structure by finding the resonance form that's the most stable, which means where is the charge most stable as it's resonating across the molecule. There's always going to be a place where it's more stable unless it's completely the same everywhere. So here I have a positive charge. We'll have three different states. Okay, we'll talk about these after, but I have positive charge on oxygen and positive charge on nitrogen. Based off of electronegativity, which is increasing as I go in this direction and is increasing upwards. Okay? Based off electronegativity, nitrogen versus oxygen. Which one is better at holding a positive charge? As I go in these directions to the right and to the top, I'm more hungry for electrons, to put it in a simple way, right? I'm better at holding negative charge. I want negative charge, right? And I go this direction, these things are better at holding positive charges. So the nitrogen in this case is better than the oxygen at holding this positive charge. So this would be our major form. Now, I know I skipped these other ones, and there's a reason why I skipped them, because the first requirement before we even look at atoms, right? I look at octet. Is the positive charge being held in an atom that has a full octet? If this case is not, this first checkbox is not satisfied, I know that, and I have other locations where I have an octet and the positive charge is there, then I know right away that these non-octet forms are not the most stable. This is the first thing that the atom, it's like the prerequisite before I look at anything else. It's the most important thing. So I need to have a full octet before I start comparing atoms and electronegativity and size and whatever. Okay? So that's the most important thing. Okay, so octet is far more important than looking at electronegativity and size. Okay, now let's say I was in the case where I had, this, and I had, actually I don't want to use positive charge, I want to look at negative charge. So let's say I had this, I had a negative charge, and I had this, right? Which one is more stable, the oxygen or the sulfur? Well, now that they're in the same column, right, I compare electronegativities when they're in the same row. So I can compare this one's electronegativity to this one because it's very significant at that point, right? The size is the same. It's very similar size. But once the size changes a lot after I go down to the next row or down the column, the size, the weight, the atomic weight of each atom is increasing. So although sulfur has a lower electronegativity than oxygen, this one is far more stable with this negative charge than this oxygen is. Okay, I'm just looking at negative charges. Positive charge is a different case. This is applicable to negative charges. So the sulfur handles the negative charge better because it's bigger, it has a bigger shell. So those electrons have a lot more space to move around and to occupy. So it's less charge. It's less charge in a certain area. So we have a bigger area for amount of charge than the oxygen does. Okay, that's usually our main situations. All right, let's look at the next one. Let's see. Okay, so the next problem is this. Okay, I'm gonna suck at drawing this. Let's see, need to. Yeah. Okay. All right. Let's see. That's our shape for now. Okay. And I have bonds right here, and I have the oxygen, whatever. I have the positive charge right here, and I have carbon coming off. Okay. So this is our molecule, and I have to resonate this. So a lot of you guys had difficulty with this one as well, and it is tricky. Now I want you to we want to consider all the options like we did before. Okay. So in the previous one, I looked around and I saw what was there. Right. I put my lone pairs on everything that has lone pairs, and you see your charge, and you look around. You know what's on my molecule. I have 2 double bonds, and I have a lone pair. I have lone pairs on the oxygen. Okay. So now, okay, sorry, the page crashed. So now, okay, I have my lone pairs of my oxygen. I need to look at what is available that I can resonate to this this positive charge over here, to these bonds over here. So this one or this one. Can't do anything with the oxygen right now, but probably will. So I have 2 options. I can either resonate this one and go in, or I can resonate this one. So how do I know which one is the more correct one? Right? Before we had 2 different paths, right? And that worked because I had a linear molecule, right? And I could go from one side and then go back to one state, and I can go from another side and go back to the original state. Okay? So it kind of worked out. All the resonance states exist, but I kind of want you to draw the primary one, not get caught up in the random ones. Okay, and you'll see what I'm talking about. So let's just draw the 2 ways that I saw in the test, and the 2 ways that you can do over here at first. The first one, let's just do this. Let's call this A. It's not an A, but pretend it's an A. All right. So I resonate this over here. Positive charge moves over here, right? I broke this bond. Positive charge moves over here. Still have this guy, and I still have this over here. All right? Make sure you draw it correctly the same way every time. You can lose points on the exam for drawing it wrong. They're not going to be like, oh, yeah, I knew what they were talking about. And they will take off points for literally anything. So just be very careful as you're drawing this. All right, so this is path A, it gives me this molecule. Path B is if I do this, okay? If I do path B, okay, so I have this, and I have this, and I resonated over here, so that means the positive charge is over here now, and now I have this double bond still over here. Okay, so these are my 2 forms. Now I'm going to look quickly at how does this progress. Okay, so from here, let's do this one first because I'm just going to tip you guys off. This is the path that I don't like as much. It's not as good as this path, and we'll see why. The next step left is I move this bond, I move this one, I moved it over here. What's left now, and to avoid going back to the same thing, I have to move this one up here, right? That's all I can do. Okay, so let's just draw that really quick. This, okay? So now, where's my positive charge? My positive charge is over here. Wonderful, cool, okay? The problem with this path, okay, is it doesn't utilize the oxygen. So now I've closed myself off from being able to use the oxygen, which we'll see is gonna lead us to getting the major form of the hybrid, okay, of the resonance structure. So if I do this structure, I move this one over here. This is path A. Move this one down here. The other option left is to move this over here. Okay, so if I move this one over here, all right, I'm gonna get this. I'm gonna get a bond over here. I'm gonna get a positive charge right here on this carbon, and I'm gonna get this. Okay, this is what I get. The oxygen's over here with its lone pairs, and now the oxygen can reach the positive charge. So this opens me up to the next one. Okay, so the oxygen can resonate in. And this is important to reach this form, right? Because this is the only form, this one right here, where I have octet on all the atoms in this molecule. And all the previous ones over here, every single one had a positive charge on a carbon, which was obviously missing its octet. So none of these forms had a full octet. This is the only one out of all the resin structures where you have the full octet. So this is the major. Okay. Now I can show both paths. Nothing wrong about it. But let's just see where this goes. Okay. Just so I'm not saying anything incorrect. Let's just see. Okay. So I move this one over here, right? And now I have to move this one over there again. So this one, this is here, and this is here now. And now where's my positive charge? My positive charge is here. So it's one more step. It gets you to over here. So this one utilizes you get to the oxygen faster. It doesn't close it off right away, but you get to the oxygen faster in this one. So I think so. Let's see, 1, 2. Yeah. So this one takes 3 forms until I get the carbon over here. This one only takes after one. I draw one other form, 2 other forms, and then I get the carbon over here. This one takes 1 other form, 2 other forms, the 3rd form. Finally, I get that. So this one's much faster at getting you to your carbocation right next to the oxygen. It's not wrong if you did this way, but I think this way requires less energy if you have less forms. Okay, I might be wrong about that, but I think this is the more correct one. I can ask Renee about that later to double check, but I believe so. Okay. But the most important thing, I don't think you would get points off if you did the other one exactly. Just you have to do all the forms until you get to the major one, which is this one. This is what we want to see. And eventually you would get to this, the same one. This just takes more. Okay. But I would have done this. Okay. All right. So I'll ask about that one, but I'm pretty sure this is the correct way. All right. Now last resonance problem. Last one is like this. All right, and I had a negative charge over here. They just drew a negative charge, but that means when the negative state for a carbon is a lone pair on a carbon. So I have this lone pair here, and that's not drawn, but you have to know that it's there. Okay, so now I have a resonance problem with a negative charge. Now, when I have this, my first thing to do is to fill in all the lone pairs and then look where I have double bonds and lone pairs. So I have over here lone pairs on this oxygen, and I have 2 double bonds. Okay, so you keep that in mind, and that will help me, make a good, it gives me good foresight about how many resin structures I have. Okay, so I have a lone pair over here, I have a double bond. They're adjacent to each other, right? So I can move this lone pair in here, and this will move out on top of here. Okay, I do 2 arrow shifts at a time, no more than that. I don't just go over here, then over here, then over here, and just do the whole thing all in one. Do one at a time. So this one gives me this. Sorry, it's small. Okay, so I have the double bond over here. now, and then I have the negative charge over here. Every time you need to draw the charge sign, it's required for you to draw the charge sign and to show where the charge moves. So positive and negative, you need to draw them every time. So I have the lone pair over here, and now can I do anything else? Yes, so I have another double bond. It's over here that I can move it to. So I'm gonna, whoops, too much. So I move my lone pair right there. This is gonna move out over here. Okay, double-headed arrow. So double bond right here. Double bond right here. And I don't have a double bond right there. And then I have, before I had 2 lone pairs, now I have 3 lone pairs and a negative charge. Okay, do I have anything else that I can do? No, I'm done. There's nowhere else to go. Put it in brackets. And this is our resonance. Okay, now what is my major form? So now I have negative charge on a carbon, negative charge on a carbon, and negative charge on oxygen. Okay, so in terms of our table, have carbon, nitrogen, oxygen. Oxygen obviously has the highest electronegativity compared to carbon. So I want if I have a negative charge, I want it to be over there if possible. So as you can see, we have the negative charge over here. Everything has octet, so we're not looking at that, right? So now I'm just comparing the atoms and their electronegativities because first of all, they're in the same row, so I can do that. I can compare electronegativities. So oxygen has the higher electronegativity, so this is the major form. Right? So we're done with that, almost done with the quiz. All right. Last question was the bonus, okay, but we covered it that day in class. So the bonus was a acid-base equilibrium problem. All right, CH3COO minus plus CH3 CH2OH and gives us CH3COOH, okay, plus CH3CH2O minus. All right, this is our this is our reaction right here. Okay, so what I asked you guys is to just, well, actually the arrow was not there, so disregard the arrow. Okay, there is no arrow at the moment. I asked you to find the direction of this arrow. Okay, so where does the arrow lie? Is it to the left, to the right? Where does the equilibrium lie? Which is just a fancy way of saying which side has the more stable molecules, right? Because my reaction is going to go towards the lowest energy states of the molecules. So whichever side is lower in energy, that's the side I'm going to favor because it's easier to achieve. You know, it requires less energy. It's more what's it called? I can't remember the word right now, but it's more favorable. Okay. Okay, so how do I determine which side is going to be the more favorable side? So normally she doesn't give you all this. Normally she just gives you one side and you have to draw the conjugate base and conjugate acid, right? But what we do is we compare the 2 molecules that have charges on them. Compare the 2 bases in this reaction, this reaction over here. Okay. But before I do that, I need to be able to compare them. I need to draw them out. So this is where being able to draw Lewis structures is important. And usually you don't have anything too crazy for these Lewis structures. But if you remember earlier, I said the COO, that's this structure, right? That's what it looks like. Okay, it's negative, so that means the oxygen has all its lone pairs. So I have a CH3. Okay. carbon, double bond O, have the O minus, right? And then added to it, I have a CH3, CH2OH. So I'm just going to use line angle, have a CH3, the CH2, OH. Alright? And I'm actually going to redraw that. Draw it out. Draw the bond. Alright? For learning purposes. And this is the blank for the reaction, the arrow line. And it forms. How do I know if I wasn't given this, how would I know what it forms? And she only gives you this. So the first step is to determine what is your base, what is your acid, okay? So basic definition, base, acid. An acid is able to donate a proton, a base accepts a proton, okay? So my base is clearly this one over here, even has a negative charge. And my acids over here, I drew out the hydrogen that's being donated. It's over here. Okay, so first step always is locating your base and acid and finding where is your acidic hydrogen. And I'll go into the concepts of what is a acidic hydrogen. But it's usually pretty easy to see. Anything, you know, OH is acidic, SH this is acidic, you know, HCl this is acidic, you know. So these are your acidic protons, usually things that are hydrogens coming off of oxygens and sulfurs and even nitrogen, but less so acidic. So as my base, this is my acid, and what happens essentially is the base takes this lone pair, and I'm gonna draw an arrow. Okay, this is a reaction. Okay, you don't have to know this at the moment. You don't have to show this on the exam, I believe. But what happens is this lone pair comes over here, and it's forming a bond with this hydrogen. And as it's forming this bond with this hydrogen, this bond is being broken. Okay, and it's going to go to the oxygen. So this oxygen, what happens is this forms a bond with a hydrogen. So I have a hydrogen here now, and then I'm gonna take this whole bond and it's gonna go back to the oxygen. It's gonna go to the oxygen, I'll go back to it. So I'm just gonna draw this on line angle now, since you've seen it. Looks like this. So this is the CH3. This is the next carbon. It has the double line O, and it has this O over here, and I drew it as a bond with a hydrogen now. Okay, so it was negative before, now it's neutral. And what does this form? This forms over here the oxygen that got another lone pair. So now this is negative. So the negative went from this molecule to this molecule. And now all I'm doing is I'm comparing the two molecules. Okay, I'm comparing them. And now I have to compare their stabilities. Which one is more stable? Alright? So I'm going to do that on a new page. We'll compare them like that. Right? So the first molecule, I'm comparing the two bases because I want to look at where the charge is, right? Those are the more unstable molecules. So I want to compare them, right? To help me find what is the major, you know, the predominant product for this reaction. What's going to form? Where does the equilibrium lie? So there are two basic forms over here. And now how do I compare them? I have a mnemonic for that. R. Okay? It's mainly these three letters. There's S, there's R's, but it's mainly the first three. Okay? In this scenario, okay, how do I know which letter to look at? What am I gonna start, you know, comparing? At this point, I see I have two oxygens, so I have the same atom, right? So the first letter of this represents for atom. So I'm not looking at atoms since they're the same. There's nothing comparable about that. Nothing cool here. That's interesting. Next thing is resonance. Right? Resonance. I'm just going to put res. Now, do I have resonance? Do I have resonance on this molecule? This is a full octet. This is full octet. You know, right here is a full octet. So I don't have any resonance on here. So no resonance. Ew. Okay. No resonance. How about on this molecule over here? I have a lone pairs and I have a double bond. So I can resonate. Okay. I have a double bond that's adjacent to a negative charge. So I can move this lone pair in and move this double bond out and move it onto this oxygen. So this can resonate, and it just resonates and it just flips to this one. The oxygen now, this oxygen on top has 3 lone pairs, and then this one now has the double bond, and it basically just looks like the same molecule, just it's flipping between these 2 oxygens. Okay, so this one has 1 resonance structure. Okay, this one has 0. So when I compare resonance, which one is better? This one is better, because the more resonance I have, right, the whole function of resonance is to stabilize a molecule, right, to delocalize, right, a very important word, write it, to delocalize, right, my charge. So the charge is moving from over here to over here, and it's going to keep doing that, you know, over and over and over and over and over. Whereas this one, the charge is fixed. It's fixed over here. Okay. So now that I've determined which one is more stable, right? We determined this molecule is more stable than this one. What does this mean in regards to our reaction? Okay. So reaction started off like this. Right? Hope everyone can see that. I'll put a blank, right? I don't know which way it's going to go right now. And it forms this. Right? So I have negative charge over here at first, and then negative charge goes over here. Make sure you draw your charges. It's very important. It's part of the points. Okay? This is a negative charge. Right? I said that this molecule is more stable than this one. So that means this is lower energy, and therefore the equilibrium is going to go in this direction. It's going to want to form this molecule. So what this means in terms of the strength of the acid or base? What this means is that in terms of comparing these bases, which one is stronger, this base over here is weaker. Really hard to draw. Weaker than this one over here. This is the stronger base when I'm comparing these two. This one's stronger. It's stronger because I'm going to write it. Stronger because it is more unstable, aka higher energy, than the other base. Okay? So because it's higher energy, it's more unstable, that means it's going to be a stronger base, right? What does a base do? It takes a proton, right? It abstracts a proton from a site that has a available acidic hydrogen, right? So it takes that hydrogen to stabilize itself. It goes from a negative charge to a neutral. The more unstable that molecule is, right? The more unstable it is, the worse it is at holding this negative charge on itself. The more strong it is, the more aggressive it's going to be to go and try and get a hydrogen from somewhere, right? It's going to really want to go and get a hydrogen. So that makes it a stronger base, and therefore, you know, the reaction is going to go in that direction. So if I had to say, oh, which one of these two bases is going to be, if they had to fight over a hydrogen, which one's going to win? Which one's going to be more aggressive? This one, which is more stabilized from resonance, it's lower energy, or this one that has no resonance, just on its own, just an oxygen with a negative charge. This one's going to be more aggressive, and it's going to be able to get the hydrogen, more than this one will be able to. Okay, so that's a dumb way of saying it, but this means that the equilibrium will go in this direction where this one becomes protonated and this one becomes deprotonated. Okay, So this one will more likely give up its hydrogen to this one and form a negative charge, and this one more likely want to become neutral rather than give up the hydrogen. Okay, so I hope that makes sense. If you have questions about it, you can just email me or ask in the group. I'm more than glad to give more examples. And that's usually, resonance is the biggest thing that you compare between bases. All right, so the steps for this is draw your molecules if they aren't drawn for you already. Look for and then start comparing them, right? Well, before you actually start comparing them, so draw them out, then look for the acidic hydrogens, right? The acidic hydrogen is going to be removed, and it's going to go to wherever the negative charge or wherever the base, it's going to go to the base, right? And then that's going to help you form your conjugate acid, conjugate base, and then from there, you're going to compare them. You're going to compare them using either atom, resonance, and this one I'm going to talk about before I finish. And this one's not really used. This is just orbitals. This is you're gonna compare the the hybridization, but not important. It's not gonna be on her exam for sure. If it is, we can always look at it. Okay. So in this case, we had resonance. Some cases you'll be comparing different atoms. When you compare atom, it's when I have an oxygen and this one is a sulfur, for example, and then I'm going to compare oxygen and sulfur. And usually she won't combine too many things, like she won't have to compare both atom and resonance, right? So usually just you compare one thing. All right, and before I finish, I'm just going to show you guys what the E looks like, how that works. So let's say I had two molecules, right? All right, I have this molecule over here. I have a carbon that has a negative charge. All right, and let's say versus, that's way too big. I have this one. Okay, same thing, but I had a chlorine over here. Let's say I have two chlorines. I'm just gonna overdo it. Whatever. Two chlorines. Now, your guessing ability might just say, oh yes, this is the weaker base, right? If you had to compare. But why is that? Well, the reason for that is this one has nothing to stabilize. There's no resonance. They're the same atom, and there's no resonance over here, same atom. But what's happening is chlorine is very electronegative, and like I said, those electronegative molecules, they pull electron density towards them. So what's going to happen is these chlorines are going to pull the electron density in this direction towards themselves, right? I'm going to have a net movement of electrons in that direction, right? And those electrons are going to be moving over the sigma bonds. It's not going to be an actual resonance where I move over a double bond, right? So because of this, these are helping delocalize the charge across the molecule. So this is called inductance. When I have a this effect where I'm pulling electron density across the molecule, but not directly moving bonds and electrons. Okay, it's more of a pulling action, right? So because this is here, this is helping stabilize this negative charge. Because this negative charge is being stabilized, that means this is the weaker base, right? So stabilizing the charge equals weaker base, all right? That's what it means, right? And AKA stronger acid. All right, and we'll talk about we'll look at acids more directly. We've been comparing bases so far. All right, so now let's look at acidic protons just to really nail the concept home. So what is an acidic proton? Okay, there's a reason why that we have very common types of why we have certain atoms always, why we have like OH and we have SH and we have NH, always the hydrogen, right? Protons or hydrogen, acidic hydrogen. And there's a reason why this occurs, why these are more acidic than, CH, for example. The reason for this is also because of electronegativity. So let's look at oxygen, for example. Oxygen is very electronegative, and what it does, electronegative atoms, they like to pull their charge inductively, right? Inductively to themselves, right? They like to pull electron density toward themselves. So what's happening is, this is also, if you understand hydrogen bonding, this is essentially how it works. But we're looking at acids here, and we're looking at so this setup, right? Also works for SH, also works for chlorine, right? Bonded to a hydrogen. All these atoms are pulling electron density toward themselves, and what happens when this happens is I'm forming a partial charge on this hydrogen and a partially negative charge on this these other atom, right? It's just a symbol for partial, right? Partial negative, partial positive. So when I make something partially positive, that is making that region more, it's making this hydrogen more acidic. And all this means that something that's negative and needs to stabilize itself, it's going to be more readily able to attack that hydrogen and abstract it. Okay, and it also means that this process of when it gets abstracted or removed, that this lone pair is going to come over here, and this is more likely to occur. So you have both the attacking part, so making it a site that's positive, right? Because negative is going to attack the positive. Okay, we'll learn about this more in reactions. You'll see it. The negatively charged things, so like I showed in the previous one, we had, we started off like this. I have the negative charge over here, and then I had the other one like this, and I had the negative charge over here, and this came and attacked this hydrogen, and this bond went to the oxygen. So that's what's happening. This is a partially positive hydrogen. It's acidic. Okay, this is basic, right? It wants to be stabilized by taking that hydrogen, forming a bond with the hydrogen. So that's essentially what's happening here. Okay, so if anyone was confused about that. That's pretty much it. I think that covers almost everything. On Saturday, I'm going to post another video that's going to go over new concepts, so not the old stuff. This is just, if you're having trouble with quiz, which a lot of you did, email me, please. I encourage you to, and to come to the office hours that I'm going to be holding tomorrow. All right? Thank you guys for watching. Hope it helped.